Voice assistants, self-driving cars, home appliances, health monitoring, industrial sensors, and wildlife tracking all have one thing in common: machine learning. In this course, you'll learn how to use simple tools to prototype ideas with machine learning. After a quick introduction to concepts, you'll jump right into designing and developing a voice-driven prototype. You'll set up the tools and hardware you need. Then you'll collect data, train a machine learning model, and deploy code for your prototype. This course is designed for anyone who wants a hands-on introduction to prototyping machine learning applications on devices with embedded microcontrollers. We begin with a brief introduction to machine learning concepts. This is followed by a quick overview of prototyping and a plan for the prototype we'll build during the course. After this setup, we'll dive in and download an easy-to-use development environment and connect to our development board from Arduino. Finally, we'll dive into the mechanics of building a learning model with a tool called Edge Impulse and use it to complete our prototype. The course doesn't assume any background in machine learning, and I'll try to explain the necessary concepts when needed. The prototype itself requires programming a microcontroller. If you have some background with programming, especially with microcontrollers on a platform like Arduino, it'll be easy to understand. However, all of the programming steps are explained, so even without experience, you should be able to follow along. In addition to software tools, the course uses a development board from Arduino called the Arduino Nano 33BLE Sense. This board has a range of sensors for many prototyping applications, including a microphone which we'll use for our prototype. It connects to your laptop or desktop using a USB cable for programming. There are currently two versions of the Nano 33BLE Sense board, the original one and a more recent revision 2. Luckily, you can use either one for this course, but some of the sensors are slightly different, so in other applications you may have to make adjustments. No matter which board you use for building your prototype, the workflow will be similar to the one we follow. We'll be collecting voice samples to use in our prototype. You can do this using the development board, but we'll focus on using your computer or a mobile phone if you have access to one. Finally, you should download the course's exercise files, which contain data and examples that we'll use during the course. So with that, let's get started. This is a course about machine learning. In particular, machine learning on what's called the edge. So what is machine learning? And of course, what do we mean by the edge? Well, machine learning is part of artificial intelligence. Artificial intelligence, or AI, broadly refers to systems that allow constructed things or machines to act smart. But what does it really mean for something to act smart? Through experience, a self-driving car learns to recognize and respond to situations like staying on the road or stopping at intersections. And chatbots analyze vast amounts of text in order to engage in dialogue and answer questions. Gaining knowledge from data and experience, when done by computers, is called machine learning and is one thing that makes them smart. But what about machine learning on the edge? What does that mean exactly? Well, the edge we're talking about is the edge of a computer network, the part that's in close contact with the real world. It used to be it was all edge. There were no networks. A single mainframe computer took inputs and generated outputs. Now it's really all about the network, a sprawling collection of computers, large and small, all connected through networks from personal and local area networks to the internet. As the surface of these sprawling networks has expanded, the devices at the edge, the ones closest to the real world, are often called edge devices. While central computers can have large or multiple processors and easy access to power and reliable communication bandwidth, edge devices usually contain embedded microcontrollers and are much more limited. Because of these constraints, in the past, data from the edge has been collected and sent over a network to larger computers for machine learning tasks. But embedded microcontrollers have become much more powerful and efficient, and learning on the edge is possible and has advantages. The first advantage is latency, the time it takes for data and results to travel across a network. Even small latencies can be catastrophic for self-driving cars, for example. Moving machine learning to the edge means results and actions are available without worrying about network latency. Next is reliability. With centralized computing, if the network goes down, so does your application. Edge devices can be designed to work with intermittent or no network communication. Networks may require significant bandwidth to transmit data, especially video. This might be unavailable to devices in remote locations, or constant communication could require significant power. An edge device that can handle many tasks locally significantly reduces bandwidth requirements. Apart from bandwidth, sending large amounts of data to a central computer can create privacy concerns. That's one reason voice assistants use wake words that are processed locally. Then only the audio required for a specific request is sent over the network for recognition. Finally, maintaining connectivity and infrastructure for centralized computing can be costly. Moving functions to the edge can help reduce or eliminate some of these costs. While designing and engineering machine learning solutions that work reliably in the field can be complicated and time-consuming, prototyping products and ideas can be a quick way to gain understanding of technology and issues as product design and engineering progress. For the rest of this course, we'll focus on the process and tools for prototyping machine learning on the edge. There are several key elements that are essential to the process of machine learning, including a model, data, training, and inference. A model in machine learning is a mathematical representation that can make predictions or decisions based on input data. The model is trained on a data set, and its performance is evaluated based on its accuracy on new, unseen data. For example, a model might predict whether an image shows a canary or a goat. Data is the fuel that powers machine learning. Without data, it would be impossible to train models or make predictions. Data can come in different forms, including text, images, audio, video, and data streams from a wide assortment of sensors. In order to be useful for machine learning, training data must be properly cleaned and pre-processed, and the data is usually labeled with the class it represents. The quality and quantity of the data used for training can have a significant impact on the performance of a model. Digital signal processing, or DSP, is a key component of many machine learning algorithms, particularly ones that deal with audio, video, and sensor data. DSP techniques are used to extract features from the data, such as frequency, amplitude, and phase. These features are then used to train models that can recognize patterns in the data. Training refers to the process of using data to teach a model how to make predictions or decisions. During training, the model is exposed to a set of examples, and the model is adjusted to minimize the difference between the model's prediction and the desired output. This difference between prediction and output is measured by a loss function. During training, the goal is to minimize the loss function, which means that the model is getting closer to the correct output. The training process repeats until the model performs as well as possible. The repeats are referred to as epochs. Once the loss function is minimized, the results can then be evaluated to determine if the model's performance is adequate. Inference is the process of using a trained model to make predictions on new, unseen data. During inference, the input data is passed through the trained model, and the model produces an output based on the patterns it has learned during training. Inference is typically faster and computationally less intensive than training. In edge machine learning, training and model development are usually accomplished on larger computers. The resulting model is then minimized and used on an embedded system along with DSP feature extraction to make inferences on incoming data. The elements of machine learning are all critical to the success of a machine learning project. Training, data, DSP, loss functions, ethics, and inference all play important roles in the process of building and deploying machine learning on edge devices. By understanding these elements and how they interact, you can better understand the systems we'll be using for our machine learning prototype. Machine learning applications, especially ones for embedded devices, typically involve evaluating input from a sensor and assigning it to one of a set of classes the device expects. A typical machine learning workflow involves several steps that are critical to success. The general steps in a typical machine learning workflow are problem formulation, data collection, feature engineering, training, evaluation, and tuning, and finally deployment. The first step in a machine learning workflow is to define the problem that needs to be solved. Identify the business or research problem that the machine learning model will address, as well as the data and resources required to solve the problem. The next step is to collect and prepare data that will be used to train the machine learning model. This requires identifying relevant data sources, collecting the data, and cleaning and pre-processing the data to identify mislabeled values, outliers, and other errors. The third step is to perform feature engineering, which involves selecting and transforming the input data into features used to train the machine learning model. This step is critical to the accuracy and performance of the model. The fourth step is to select an appropriate machine learning algorithm and train the model using the prepared data. The fifth step is to evaluate the performance of the machine learning model. This involves using various evaluation metrics such as accuracy, precision, recall, and F1 score, then adjusting the hyperparameters to optimize the performance of the model. The final step is to deploy the trained machine learning model in a production environment where it can be used to make predictions or decisions. This involves integrating the model into a software application or system, monitoring its performance, and updating it as needed to ensure that it remains accurate and effective over time. Overall, a typical machine learning workflow involves several iterative and interdependent steps, from problem formulation to model deployment. By following a systematic and data-driven approach to machine learning, it is possible to build accurate and effective models that can address a wide range of business and research problems. Ethics and machine learning are closely intertwined, as machine learning algorithms have the potential to impact society in profound ways, both positive and negative. As machine learning is increasingly used to make decisions in areas like healthcare, criminal justice, and finance, it's important to consider the ethics of these systems. A key ethical concern with machine learning is bias. Machine learning models are only as good as the data they train on. And if the data is biased, the model will also be biased. For example, if a machine learning model is trained on data that includes only male doctors, it may not be able to accurately predict the performance of female doctors, leading to biased decisions. Another ethical concern with machine learning is privacy. As machine learning models are trained on large amounts of data, there's a risk that sensitive personal information could be exposed. For example, if a machine learning model is used to predict which patients are at risk of developing a certain disease, it could inadvertently reveal sensitive information about the patient's health. Transparency is also an important ethical consideration in machine learning. It's important for machine learning models to be transparent and explainable, so that users can understand how the model is making decisions. This is particularly important in areas such as healthcare and finance, where decisions made by machine learning models can have a significant impact on people's lives. Fairness is another important ethical consideration. Machine learning models should be designed to treat all individuals fairly and without bias. For example, if a machine learning model is used to make hiring decisions, it should not discriminate against individuals based on their gender, race, or other protected characteristics. Accountability is another critical ethical consideration in machine learning. As machine learning models are increasingly being used to make decisions that have significant impact on people's lives, it's important to ensure that the decisions made by these models are transparent and accountable. To ensure this, there should be clear lines of responsibility and oversight for the machine learning models, and users should be able to challenge and appeal the decisions made by these models. A final consideration in ethical machine learning has to do with unintended consequences. Applications with innocent intentions may be appropriated with less innocent objectives. For example, an application that collects wildlife tracking data might be misused to track human populations targeted for control or abuse. Ethics and machine learning are closely intertwined, and it's important to consider the ethical implications of machine learning as it becomes increasingly ubiquitous. By consciously and continually addressing ethical issues, you can help ensure that machine learning is used to benefit society and promote the greater good. This course focuses on prototyping applications using machine learning on devices that live on the edge between networks and the real world. While documents, designs, and images are important in the product development process, there's nothing like having a tangible working prototype. Depending on your project, a prototype can take the form of anything from a static screenshot to a 3D printed model to a functional prototype of a physical product. In this course, we'll be working on a prototype that incorporates machine learning to recognize keywords. 3 general reasons for prototyping are exploration, communication, and evaluation. Especially when you're working with new or unfamiliar materials and technology, building a prototype can help you explore and gain a better understanding of the potential and challenges you might encounter. Communication is one of the most crucial elements of any project, and communicating a design or product idea to team members, project stakeholders, and customers is one of the most powerful reasons to build a prototype. Much more engaging than a static document or presentation slides, working with a prototype can impart a visceral understanding of a product's vision and experience. The final reason to prototype is for evaluation. The adage, "test early and often," is true of almost all product development. Even before underlying product technology is developed, prototypes can be used to get feedback from stakeholders and customers about product features and experience. Modifying a prototype in response to feedback and presenting it for another round of evaluation is crucial to iterative design and can help save time and resources in engineering a final product. I've mentioned that communication is one of the reasons to build a prototype. But if you're presenting a prototype to others, it's important to be clear with yourself and others the purpose of your prototype. 2 of the most common fails of prototyping are: a stakeholder sees a high-fidelity prototype and believes that product engineering is complete. Or, a stakeholder sees an exploratory prototype and believes the product brief has been ignored because the prototype doesn't resemble a finished product. Communicating a prototype's intent before presenting it is the easiest way to avoid misunderstanding and ill-placed expectations. One final point is that product prototyping and engineering are different. While a prototype may help inform engineering, the goal of prototyping is to create inexpensive examples of technology or experience that can be easily changed or adjusted in response to feedback and changing requirements. Engineering a final product, on the other hand, must take into account many factors including reliability, cost, and schedule, as well as ethical and legal considerations. You should definitely evaluate ethical and legal implications of any product during product design and development, but building the prototype may actually help with this. When starting a prototype, it's best to begin with an understanding of what you're trying to accomplish. In our case, let's say that your company's marketing department has identified an opportunity for a next-generation keyboard that supports voice-activated keyboard macros. For example, saying "close window" might close the active window on your desktop. The thinking is that by using keyboard macros, The keyboard could be moved between computers without having to set up speech recognition and macros again in the new computer. After meeting to discuss the idea, a team is created to investigate the technology and designs for potential products. As the developer on the team, you've been tasked with building a prototype to explore the technology and to help the team understand the experience of using voice commands with a keyboard. You're working from home, so you make some tea and begin thinking about how to put this prototype together. As you pour water into your cup, your cat Bernie hops up on your desk and, ears flattened, begins a dash across your keyboard. You cross your fingers he won't accidentally send an email or worse. The incident is alarming, but it gives you inspiration. You decide to prototype a keyboard that locks your screen when you say "shield up," keeping Bernie from doing any damage. You do some quick research and find out that some Arduino development boards support embedded machine learning and include a microphone for keyword recognition. You also discover a tool for developing machine learning designed for embedded applications called Edge Impulse. Especially in prototypes for exploring technology and experience, there are often too many variables to make an all-inclusive plan. It's better to take an iterative approach. That's the case here. Your first step is to get your board up and running with a basic program. Next, you'll run a machine learning demo to see if it works on your hardware. Then you'll move on to training your own keywords. For this, Edge Impulse is the tool that will help. Finally, you'll figure out how your development board can act as a computer keyboard connected to your computer. With that general plan in mind, it's time to begin exploring these technologies and build the prototype so you can show it to the team. We plan to program our development board with our prototype, so the first thing we need to do is download the Arduino Development Environment, or IDE. Let's go to the desktop for that. So let's start by opening the browser and going to the Arduino website. And you can see this has a lot of information about the Arduino, including its hardware, software. They have a cloud as well, documentation, a lot of information here, and their community forums. So let's go to the software tab. And here is the most recent version of the IDE, so we can download the one that's appropriate for your operating system. Mac OS is ours. You can contribute if you'd like. So now we can go to downloads to see. This is for the Mac, it's just a disk image. You can follow whatever directions are appropriate for your operating system. For me, I'll just open up this disk image, and then it's a matter of dragging the IDE. I'm just going to drag it to our desktop. Close out of our windows. I'm also going to eject this disk image from my desktop. Okay, so now we can open up the IDE and take a quick look at it. You can see that the bulk of the screen is taken up by a program. This is an empty program right here, and our prototype will end up in here. And if you want to compile the program or just verify the program, you can use this button in the upper left corner. Next to that is an upload button, which will compile this program and send it to your development board. Then here, again at the top on the right, just to the right of those buttons, you can select which board you're using. We'll use that later. Then if you continue over on the top, you can see two utility buttons on the far right. One is a serial plotter, and then one that we'll be using is a serial monitor, which monitors communication with your board. Then over here on the left is a sketchbook where your sketches are stored. Boards, we'll look at the boards manager to make sure that we have the proper software for our board. The library manager here gives you access to libraries that support different pieces of hardware or can add functionality to your code. And then there's search here. The only other thing to point out is on the bottom line is a status line, which can give you information about your compiling and the board that's connected. Okay, now we're ready to get our development board connected and try uploading a program. Now it's time to connect the Arduino development board and make sure we can upload a program or sketch. But before we do that, let's take a closer look at our board, the Arduino Nano 33BLE Sense. We're only using its microphone in our prototype, but this Arduino board is packed with features, including an inertial measurement unit, a humidity and temperature sensor, a barometric pressure sensor, a light sensor, and an RGB LED. The microcontroller on the board connects to all of these. The microcontroller's connections are called pins. Some of these pins are connected to pads on the edge of the development board so they can be attached to external circuits. Other pins are connected to onboard circuits, like the built-in LED. And pins have names you can use to refer to them in a program. Finally, pins can be either input or output. As an input, a pin might allow the microcontroller to get data from a sensor. As an output, a pin might turn an LED light on or off. Now let's go to the desktop to see if we can connect the Arduino and run a simple program. The first thing we need to do is connect our board to the computer. We do that with a micro USB cable. Notice, when the cable is connected, the power light comes on. Now let's go to the Arduino IDE to run a simple program, making sure everything is working properly. So the first thing is to launch the IDE. And one thing I'm going to do is set up some preferences here so we can see more what's going on. I'm going to set up verbose output for both compiling and uploading. And I'm also going to look at all of the compiler warnings, just so we can see. Okay, so the first thing we need to do is to select our board. And we do that with the selection box up at the top. And if you click on that, you can see the Arduino Nano 33BLE, and you can see that it's connected to a port. So that means that the USB connection is working. So I'm going to select that. Then I'm going to go up to the File menu and go down to Examples, and then over to Basics and Blink. Blink is kind of like the Hello World for hardware. Now it loads up that Blink programmer sketch. If we look at it, it's very simple. The program is divided into two sections, the setup, which is run once just at the beginning, and then the loop, which is run repeatedly. So you can see that we're referring to that LED pin, the built-in LED, and in the setup we're saying that the mode is output, so we're using it as an output. And then in the loop, we're writing to the output, and we're setting it high, delay waits for a second, 1,000 milliseconds, and then we're setting it low and delaying again for another second. So this is going to result in the light just blinking. To upload this to our board, we can come back up to the top on the left, and you can see the upload button with the arrow facing right. I'm just going to click on that, and it'll begin compiling all the bits of code it needs. And now you can see it uploading both on the screen and on the board with the flashing LED next to the USB port. Now that you've confirmed that your development board is connected and working, it's time to move to the next step and run a machine learning demo program. It's always a good idea to verify hardware works on a known example before you start working on something new. That way you don't spend hours debugging code when the problem is actually your hardware setup. So let's go to the desktop and try a pre-made machine learning example on our development board to make sure it works. So I'm going to point out, if you open up the exercise folder, which you can download from the course site, you can see in Chapter 3 here that there's a voice RBY inferencing.zip file. That's actually our sample application. It's a library, as we'll see in a second. So I'm going to open up the Arduino IDE, and in order to use the sample application, I have to install the library. And the way that I do that is I go to the Sketch menu at the top, then I go down to Include Library, then I go over and I say Add Zip Library. Now in the File Open box, I can go to the desktop and then click into Exercise Files, Chapter 3, and then choose the zip file. And I'll open that up. It says it's processing that zip file. And then it'll tell you that the library has been installed. Now you can go up here to the menu again and do File, Examples. And you can see examples from custom libraries over here at the bottom of the examples. And then you can go over to Voice RBY. If you don't see examples from custom libraries, you may have to exit the IDE and then start it up again. But we're seeing it in this case, so I'm going to load Voice RBY. This is a fair amount of code, so I'm not going to try to explain it right now. But it's a very similar app to the one we're developing, and it has 3 keywords, red, blue, and yellow, and they can be used to change the color of the onboard RGB LED. So just like we did with the blink example, first of all, we have to select our board, select the Arduino Nano, and then we just click on the upload. And it'll start compiling the sketch. It may take a while. It'll keep you appraised of the progress. We'll speed through this, but don't be surprised if it takes a while to compile on your computer. Now you can see the sketch beginning to upload, and you should also see the light on your board. Okay, so now that the sketch is running, you can test it out by saying red, blue, yellow, blue, red. And assuming that it works, then you've confirmed that you can actually run a machine learning application on this board using the microphone. So the next step is to begin developing the custom machine learning model for your prototype. To develop our machine learning model, we're going to use a web tool called Edge Impulse. Edge Impulse makes it easy to collect data and train a learning model that can be exported to the Arduino. This makes Edge Impulse perfect for prototyping. Apart from being easy to use, Edge Impulse is very flexible and powerful enough for robust commercial applications. With that, let's go to the desktop and get started building the machine learning part of our prototype. I'll start by opening the browser, going to Edge Impulse. Here you can see the main home page. There's a menu of options across the top. We're mostly interested in the developer section, which has documentation, shared projects, and a forum you can join to ask questions. Over on the far right, you can see the login links, or if you don't have an account already, you can click on Get Started in the upper right corner. We'll do that. You can sign up for an account here. They're free for developers. I already have an account, so I'm just going to log in. Enter my name. Since we haven't created any projects, our project directory is empty, so we can create a new project. Click on that button. Enter the name. I'm just going to call it Voice Commander. And it's a developer project, which is the only type we can create with this free account. And then it takes you to the project homepage or the project dashboard. And it asks you what kind of data you're going to be working with. In our case, we're going to be working with audio data. So I'll click on that. And now it gives me a wizard for how to continue. You can take a look at that, but we're going to follow our own path. Looking at the project page here, you can see in the center it gives you the project name, which you can change at any time. There's also a project description right below it. I'm going to edit that. This is our keyboard voice commander prototype. If you have more information you want to put on the project, you can add that to the README by clicking on the README button. Also, if you look over on the right, it says your project is private. It is by default. You can also make it a public project so that you can share it with other people. On the left here, you can see a list of tabs that you can use to walk through the different parts of the process of creating and deploying the model. I'm going to scroll down a little bit here. You can look at the rest of the page. You can see that it shows you the 3 basic steps of creating an application here. At the top is acquiring data. Below that is designing an impulse, which is a machine learning pipeline. And then finally at the bottom, you can deploy your model to a device. So that's it for creating your first project. In later videos, we'll look at collecting data, designing and training our learning model, and then finally deploying it to our device. Now it's time to build a data set for our prototype. We'll use a combination of recording custom samples of our keyword and uploading data prepared from other sources. Let's go to Edge Impulse to see how this works. Here we are on our project dashboard. And to collect data, we can scroll down. We can see the Acquire Data section as the first task for this project. So we can click on the Let's Collect Some Data button. And it gives us a number of choices of where we want to collect the data from. We're going to collect data from our computer, and it'll take you to a new tab with a web app for collecting data. We're going to be collecting audio data. It asks for permission to use the microphone. There are 3 parameters that affect the sample. The first is the sample's label. In this case, it should be set to shield up. Then there's the sample's length, which should be set to 60 seconds or 1 minute. You'll say the keyword over and over within that time. Finally, we want to make sure the category is set to training. When you start recording, say the keyword shield up over and over with short 1 or 2 second pauses between each time. It's best to try different ways of saying shield up and maybe get friends to record saying shield up for a varied data set. So let's start. Shield up, 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 shield up. Okay, that completes your first 60-second sample. Now you need to create a total of 5 sample files or 4 more. When you're done, you can close the tab and go back to the main Voice Commander dashboard. Now that you've recorded 5 seconds of data, we can go back to the Data Acquisition tab in the main project, and we can click on each of those samples. And you can see, you can play it back, and you can click on each one and see its waveform there. The thing is, in order to train our neural network on this keyword, we need a bunch of individual samples of the keyword. So, we're going to break each of these 60-second samples into 1-second samples, each of which contains an instance of the keyword. To do that, we come up to the sample and then click on the 3 dots to the right, and then go to Split Sample. It'll automatically isolate the individual samples. If we can zoom in here to see more closely what's going on. And you can see that it's captured each sample in a segment. Now it's showing you most of the samples are relatively centered within the segment, and that can lead to some bias in your samples if when you're sampling, it's always expecting that sample to be in the middle rather than the beginning or the end. So one way you can get around that is to check Shift Samples here on the bottom. And you can see that it moves the samples back and forth. Now here's a sample, though, that it looks like it's kind of cut off the end. So I always try to move it, maybe quickly scan through these. And most of them are okay, but some of them are a little too close to the edge. So after adjusting them, Go over here to the other side. Good. You can click on the split button down here. Now you'll notice you have a bunch of 1-second samples, all labeled as shield up samples. We can click down here. Still 1 second. Now here at the end, we can see our 1-minute samples. So let's go ahead and split those samples as well. Okay, so now instead of having 5 1-minute samples, we have roughly 2 minutes and 21 seconds. That's 141 1-second samples. So that's a relatively small sample set for training, but for a prototype, it might be okay. Now, in addition to our keywords, we want to add some background noise as contrast. So we want a bunch of samples of just background noise. So when the network is being trained, the learning network is being trained, it can differentiate between just normal room sounds and our keyword. You could go and record all of those samples yourself, but we've also provided these set of samples that you can upload. And so you can upload them from the exercise files by clicking on Upload Data, and then navigate to the desktop, Exercise Files, Chapter 4, Datasets. And we've provided both 100 sample and 200 sample datasets, but let's go with the 100 sample. And in fact, we provided a bunch of shield up samples just in case you didn't want to record your own. But here are the noise samples. So we're going to open that folder up, and we can select all of these and upload them. We want them to go in training just like the samples we recorded. And now begin upload. So everything was successful. Now if we go back to click on the Data Acquisition tab again. Okay, now you can see we've got 4 minutes and 1 second. That's almost double the samples we had before. And you can see these new ones are labeled as noise samples. So now we have 2 sets of samples, 2 labels, one for shield up and one for noise. The next thing we'll do is we'll create a learning model and look at training that with these samples. After building a data set for your prototype, it's time to set up the learning pipeline or impulse for processing and classifying the data. Let's go to Edge Impulse to see how that works. Here we are back on the Voice Commander dashboard. In order to set up an impulse or a machine learning pipeline, we have to have data. So let's just click on our Data Acquisition tab, and here are all the data samples that we collected earlier. Next, we just go to Impulse Design. The impulse consists of an input, which identifies the type of data. In this case, you can see it's already set to audio. Then we need to add a processing block to extract features, and then a learning block to learn the features and output classifications. Okay, so the first thing we do is click on the Add a Processing block. There are 2 recommendations from Edge Impulse for audio data. The first one is for human voice, and so we'll take that one. Then we go back here and add a learning block. There's only one classification block that's recommended by Edge Impulse, and that's useful for recognizing audio, so let's add that one. Then all we have to do is save the impulse. And that's it. We're ready to go on to training and seeing how this performs. After collecting our data and creating our project's impulse, the next step is training the learning model. So here we are on the project's dashboard again, and there's one thing we should do first. If you scroll down to the bottom of the dashboard on the right-hand side, you'll see that there's a target device listed here. Right now it's set to a default Cortex M4, I think at 80 megahertz. We should set it to the board we're actually using, which is the Arduino Nano. That'll give us better estimates of the time it's taking, or it will take when we deploy this to the board. So now I'm going to go back up to the top of the dashboard, and then there's one other thing we need to take care of, which has to do with the data. So if we go over here on the left to data acquisition, you can see the samples that we've acquired. If you look up here at the top, though, you can see kind of a triangle warning. And if you roll over it, it says one or more of the labels in your data set have a poor train test split. So I'm going to click on that. What that means is when you're training a learning model, you typically want to test it after you've trained it against data it hasn't seen. So what you typically do is you collect all of your data, and then you put most of it into your training data set, but then you put part of it into what's called the test set. Right now, everything we have is in the training set, and the split is typically 80% training, 20% test. And down here, it gives you the option of actually performing that split. So we're going to go ahead and do that. And it wants to confirm that that's really what you want to do. And then it wants to confirm even further. So we'll let it know, yes, that's entirely what we want to do. Okay, and now it's happy. It's showing 80% here is in training, and then 20% is in testing. Okay, so now we can proceed with training the network. So we'll come down and click on our impulse, just where the learning network is. And we added two blocks, as you recall. One was the audio processing block, and then we have a classification block, which results in two different classes, noise and shield up. So let's go and configure those blocks. So if we click into the audio block, it shows us some options here, and it shows us what's going on. The audio processing block creates Kepstrel coefficients, which is a spectrogram across your whole sample and with specific frequency bands relating to speech. Here's what the spectrogram looks like for a white noise sample. It's pretty even. And we can go into our samples here. Let's choose shield up, a shield up sample. Okay, you can see that the spectrogram looks quite different. This is what the training model is training on, not the raw data, but this spectrogram. We're going to leave all the different parameters as default. But what we need to do is, for our data set, we need to generate the features so that the training block can use them. So we'll go up here and click on Generate Features, and then click the Generate Features button. So it's going to take a while to go off and do that. If we scroll down, you can see some status as it's scheduling a job to do those calculations. Okay, and the job is completed. It shows you a flattened diagram of how all of your samples end up separating. So the feature separation looks pretty good here. All of the shield up sounds are around the outside, and all the noise is on the inside. So the next thing we need to do, since we've created these features, is go here to the classification. And you can see our target is set up here. And we're going to leave the parameters to their default, just like we did with the processing block. If we scroll down, you can see that the input layer has 650 features, which is actually 50 different time segments across the 1 second sample and 13 different frequency segments. And then this shows you the architecture of your learning block, and it's going to output two classes. And so let's just start training this. Scroll back up here, and it shows you again a status of the actual training process. Now it's looking at different models and comparing results. Okay, so when it's all finished, it gives you some results on the bottom. And you can see that there's actually fairly decent separation here as well. It made some incorrect inferences. We're getting 94.7% accuracy for noise and 92.9% for shield up, which isn't bad, and it's probably fine for our prototype. If we were going to move this into production, we might approach this differently. And it looks like our loss of 10% isn't really too large either. So That's it for training. The next step is to deploy this and see how it actually performs in practice. We've trained our model. Now it's time to test it to see how it performs in some real situations. Here we are back on the project dashboard, and there are two things we can do to test it from here. The first thing we're going to do is go to Model Testing on the left-hand side, the tab. So this is where the test data that we separated out before comes in. All of that test data is listed here, and we can have the model classify all of these to see how accurate it is. So I'm just going to do that now. Click on this Classify All button. As usual, it's going to run a job to do all of this, so it's going to take a little while. Okay, so it completed the job. Let's scroll down here. So it had 92% accuracy. It missed a few. It didn't recognize this one as noise. Scrolling down. It's not a very large data set, so it only had issues with 3 different samples. We can go and actually look at the sample it had problems with by clicking on the sample, then going to Data Acquisition. Let's see. This one looks like it's right at the beginning. Yeah, and it was kind of a funny voice, so it didn't really fit the spectrogram it was expecting. But overall, it seems to have performed reasonably well with this test. So I think we can move forward. And the other way to test it is to actually deploy it, but deploy it to a computer app that doesn't require any programming and see if it can recognize you saying the keyword just through the microphone. So let's go to the Deployment tab on the left. And there are lots of different possibilities for how to deploy your model. We'll come back to one of these later. But I'm going to scroll down to the bottom. And it says Run your impulse directly. You can run it on your mobile phone or you can run it on a computer. We're just going to run it on our computer, so I'm going to click on this. And then I'll click Build. So it opens another tab and scheduling a job to build this little sample application. Okay, and it's going to ask for access to the microphone. Now it's listening. Shield up. Shield up. Shield up. Shield up. So I just canceled that application, but it was actually responding to my voice, so it was recognizing the keyword. So at this point, I think we've tested our model out pretty well, and the next step is to actually deploy it to our development board. Now that you've tested your learning model, it's time to deploy it to the Arduino to see how it performs on your development board. Here we are back on the project dashboard, and we remember that to deploy it, you scroll down on the left side, the tabs on the left, and click on Deployment. Now before we scrolled all the way down and deployed to our computer, but now right at the top, we see we can deploy to an Arduino library. I'm going to click on that. There's also support for other boards or just a vanilla C++ library, but the Arduino is the one we want. So now we have to scroll down to the bottom of this deployment screen, and we can click Build. And it'll spawn a job to do the building over here on the right. This is a pretty quick process, and you can see it's built the library, and it's actually downloaded it into our Downloads folder. And that's all you have to do to build the library. The next step is to install the library in the Arduino environment. Now that you've deployed an Arduino library from Edge Impulse, it's time to install it in the Arduino environment and run an example to see if the prototype learning model works on the development board. So the first thing I'm going to do is open up the Arduino development environment. Let's go ahead and select our board. And then let's install the library that we deployed from Edge Impulse. To do that, if you remember from when we ran the sample learning sketch at the very beginning of the course, we go here to Include Library, Add Zip Library, and then we'll find that in our Downloads folder, actually. And this is the library right here, EI for Edge Impulse, Voice Commander, Arduino, Zip. It says it's processing, and the library has been installed. So we can go up here now to File, Examples, and right next to where the first library was installed, here's the new one. So let's go over here, and you can see that there are a bunch of example sketches here. And for the Nano BLE 33, let's go down here and choose a microphone sketch. Selecting the board here. I'm also going to open the serial monitor. This example does continuous voice recognition, and it prints the results of trying to recognize keywords in the serial monitor, which is why I brought it up. Let's just upload to the board. It's going to take a while to compile. Now it's beginning to upload the sketch. Now if we click over to the serial monitor, you can see that it's doing samples and classifications. There's a lot of noise. Shield up. You can see shield up has a high percentage there. Shield up. Shield up. Shield up. Shield up. There. So that shows that the classification is working, so we can go on to develop the features we need for our prototype. You've run the sample sketch from the Edge Impulse library on the Arduino development board, and you've seen output in the serial monitor showing keyword recognition. Now it's time to add some custom functionality to the sketch. For this, we'll take a small step by blinking an LED when the shield up keyword is recognized. To reduce the amount of typing required, I've included code we can import in the course exercise files. If you're following along, make sure you've downloaded them. Okay, let's head to the desktop to see how this works. First thing I'm going to do is open up the Arduino IDE. And then I'm going to open the example from the Edge Impulse library, same one we used before, the continuous microphone example. And I'm going to save this right off the bat so we can make it our own and make changes. Call it Voice Commander LED. Okay, now it's connected to our Arduino Nano board. Let's just take a quick look at this. It's a lot of code we don't really need to understand from Edge Impulse. There are a couple of features, though, that you might recognize. The first is this setup function, which runs one time at the beginning of the sketch. And we saw that in the blink example at the very beginning. Then there's the loop function here, which runs continuously from then on. So the next thing we're going to do is download our custom code, and then we'll come back and make a few changes to this example code here. So to add custom code, I'm going to go to Sketch, then Add File. Then we go back to the desktop where I have my exercise files, and then go into Chapter 6, Voice Commander LED, then custom code LED.ino. Let's open that up. And you can see that that's been added to the sketch. Okay, now in the main file, I'm going to scroll down a little bit. And the first thing I'm going to do is there's this line 69, which is a while not serial. It's waiting for a connection to the serial monitor, but we're not really going to use that because we're blinking an LED, so I'm going to comment that out. Then keep on scrolling. And actually, I'm going to scroll back up or scroll down to the bottom of the setup function around line 84 here. And I'm going to add another function called custom setup. Then I'm going to come to the loop, go to the bottom of the loop right here, do something that's pretty similar. It's called, I'm going to add a function called implement result, and then put the result in there so it can implement it. And those are the changes. So now let's go over and look at that custom code. And you can see at the top, I've put in some constants for the labels of the different classes, noise and shield up, and also a recognition threshold. So it won't respond if it doesn't recognize a label above 90% confidence. Okay, here's the custom setup that I referred to when I typed it into the main code. And all this does is it sets up the LED and flashes it 3 times, so you know the sketch has started. And then down here is the implement result function that I called. And this just makes sure that a class has been identified, it's above the threshold. And then depending on which class it is, it'll turn the LED on or off. When I say shield up, it'll turn the LED on. Anything else turns the LED off. Okay, so that's it. Let's upload this sketch and see if it works. Starts compiling. It's going to take a little while to do that. Okay, now it's done compiling and it's uploading. Should see the upload light. 3 flashes. Shield up. Shield up. Shield up. Yeah, sure enough, the LED flashes with the keyword. So that's it. Now it's on to implement the final prototype, which is adding some keyboard functionality. Okay, everything is finally in place to complete our Shield Up prototype. All we need to do is add keyboard functionality to our sketch and test it out. So let's go back to the Arduino IDE and see how that's done. I'm going to open up the Arduino IDE. And since we were just working on the voice commander LED sketch, for me that opens up. If that's not the case for you, you can come up here to File, Sketchbook, and open up the voice commander LED. Make this full screen. And now what I'm going to do is save this, because this is our starting point. I'll save it as another name. And instead of LED, we'll call this voice commander keyboard. Now we still have the custom code for LED in here, so let's get rid of that to begin with. And let's add sketch, add file, come back to our exercise files, chapter 6, 02, custom code keyboard.ino. Open that up. Now it's been added to our sketch. So we don't really need to make any changes to the main voice commander keyboard.ino. Most of that is Edge Impulse. All of the changes are in the custom code tab here. So let's just take a quick look at that. Nothing has changed. The recognition threshold is still 90%. The labels are still noise and shield up. But now we've added some keyboard libraries to support keyboard and some key definitions so that we can send specific characters to or through the keyboard. Then we create a keyboard variable here so we can use it later. Custom setup is the same, just blinks LEDs. Identify class is the same. And then here where we implement the results, it's mostly the same. It'll blink the LED when we say shield up, it'll turn the LED off with anything else. Except now when you say shield up, it adds one more thing, which is sending some key codes to the keyboard. And this says it's sending Q with the control key and the logo key, which on the Mac is the command key. So control command Q locks the screen. If you're on a Windows computer, this line underneath it should work. It's the logo key, the Windows key, and L should lock the screen. So if you're on Windows, uncomment this line by taking the slashes away and comment out this line by putting 2 slashes there. So there's one other thing, though, that we want to do with the main tab here. There are a lot of print statements in the loop. So here's the loop. So every time it goes through the loop, it prints out some information, which is really useful if that's all you're looking for. Now we have keyboard results and an LED to tell us what's going on. So I'm going to just remove these print statements. So I'm going to select the top here, and this is the bottom. So you can see all these things. And I'm not going to delete them. I'm just going to go up here to edit, and then comment, uncomment. And so that comments them all out, so they'll be ignored when the program is compiled. Okay, so I'm going to save this file, save, and let's upload it to our board and see how it works. It's compiling. Now it's beginning to upload. See the LED flashing. Now 3 flashes. Now let's try it out. Shield up. Congratulations! The prototype has met its goal of locking the screen when you say shield up, and it's protected against marauding cats. Now you can show the prototype to the team and let them know what you've learned about the technology and the process. You've done a lot of work getting to this point. Now here's a challenge you can work on to see if you can extend your prototype even further. The goal of this challenge is to add another keyword to your prototype. The word is emoji, and it should cause the emoji panel to pop up on your computer screen. Just in case you need some hints, here are a few. We haven't talked about this, but on the left panel of Edge Impulse is a tab labeled Versioning. It's a great idea to follow the instructions and save a version of your project before making big changes, just in case you want to get back to the beginning. The next hint is you can look in the exercise files for keyword data that might help, and also for custom code. The third and final hint, we haven't talked about this, but to update a zip library with Arduino, you must first delete the old library from the Documents folder, Documents, Arduino, Libraries, and then install the new zip library from the IDE. So that's the challenge. The next video will show you the solution I came up with. Good luck! It doesn't sound complicated on the surface, just adding a new keyword to your model, but this was a pretty big challenge with several pieces to it. Here's how I approached it. Started out by opening up Safari and going to Edge Impulse. Make this full screen. Make sure I'm logged in here. And here we are on our dashboard. And I mentioned this in the hint, but anytime you're going to go and make a big change to a project, it's a good idea to come down here and snapshot the current version. So if you need to get back to it, you can. So this is our first version. So this is the initial commit of the working keyboard prototype. And we'll just store this version. It'll take a second to do that. Okay, that's completed. We can see our version right here. So now we can make changes with abandon. So let's go to data acquisition. I need to upload, or I need to add samples for the new keyword emoji. And instead of trying to record them myself or with others, I'm just going to upload data from the course exercise files. So go to choose files. I'm already in the emoji, but I'm going to go back up here to the desktop, go in exercise files, chapter 4, data sets, and data 100. Choose these 100 samples from the emoji data set from the class. Come down here. It shows me 100 files. Since the data set is already split between testing and training, I'm going to automatically split the new uploaded files so I don't have to rebalance the entire data set once they're uploaded. So come down here, begin upload. You can see the job running, goes pretty quickly. Okay, so we've added the data, but now we need to go back in and retrain both our features and our classifier from the impulse. So let's click on the audio features, the MFCC block. And I'm just going to come up here to generate features and click on generate features again. So you can see there are two classes here now. Once I've generated features, it should show 3 classes, including the new one, emoji. You can see the job running down here. That's completed. Now you can see we've got 3 classes or features here. You can see that there's fairly decent visual separation between the different sample classes. This is emoji, the kind of blue-purpley ones. The orange ones in the center are noise, and then the green ones around the edge here are shield up. So now that we've generated features, let's go down to the classifier, and we have to retrain our network for these 3 features. I'm going to do something slightly different here. I'm going to choose data augmentation, and I'm going to choose low here for adding noise. And what this does is it creates kind of multiple copies of every sample with different distortions. And when you train a network with all those different samples, it gives you a slightly more robust result. So now that we've done that, let's go down here and start training. We can watch the job up here. So it's finished training the model. Let's see what the visualization is. This is pretty decent accuracy here. If we come down, you can see there's good separation between noise and this is shield up here and then the emoji down here. There are a few incorrect classifications, but nothing to worry too much about for our prototype. Okay, so the next thing we need to do, normally I would run this against the test set, but I think for brevity I'll just skip past that part of the process and move down to deployment. So we're going to deploy a new Arduino library. And we'll come down here and build this. This is a relatively quick process compared to training. Okay, that's done. And it's in our downloads folder. So let's get out of Studio Impulse. And in order to update a library with the Arduino, we have to do something that's a little complicated. So I'm going to get a new Finder window here. And if we go to Documents, Arduino, Library, you can see we've got the previous version of this voice commander library from Edge Impulse. In order to update it, we have to manually remove this. So I'm going to move this to trash. And just for good luck, I'm going to empty the trash. Yep, I want to empty it. Now we can start up I'll close this, start up the Arduino IDE. And I'm going to go Sketch, Include Library, Add Zip Library. Now I'm going to go to Downloads here. And we have a previous version and then the highest number, Voice Commander Arduino 1.0.6. Let's select that one and it's going to try installing it. Okay, now the library is installed. If we come up here, we go to examples, you can see that the library is here. So that's great. And we happen to be showing the keyboard sketch right here, which is the next step. I'm going to make the emoji sketch off of this one. So I'm going to save this as Voice Commander. I'm going to select all this and just call it emoji. Okay, so now we've got another sketch we can work with. And then, just like we did before, rather than typing everything in, I'm going to get rid of this keyboard custom code. Delete this. And then I'm going to add the custom code for the emoji sample or example. So if we go to desktop, we can go to exercise files, chapter 6, and hidden under challenge solution, custom code emoji. So let's open that. Now in the other examples, we didn't have to make any changes to the core sketch. So let's just look at what's changed with the custom code. So a new label was added for emoji. A new character was added for the keyboard. The dot character wasn't here before because that's required for Windows. And let's see. The startup is the same. Still set the LED and then blink it 3 times to let you know that the sketch has started. Identify class hasn't changed. But now under implement class, we've added another if statement. So originally we just checked for noise, and if it was noise, then we would turn the LED off. If we found shield up, then we turned the LED on and sent some keys to lock the screen. And then we've added this third one down here, else if the label is emoji, then turn the LED on, and this is the key code to open the emoji panel. So those are all the changes we needed to make. So I'm going to go ahead and upload this to our board. It's going to take a while to compile this as usual. Okay, it's finished compiling. Now it's uploading. Should see the upload lights flashing on the device. Okay, and apparently recognized emoji right there. Let's close that. And I'm going to open text edit, emoji. And there you go. It pops up the emoji. And of course, when I say shield up, and that's it. So we've added a keyword, we've retained our old functionality, and we've added the new functionality. Deploying a machine learning prototype to production is an exciting way to bring intelligent solutions to the edge. However, it's not always a simple process. A first step is to optimize your learning model and make sure it performs well under realistic conditions. This will often involve redeveloping your training data using more samples and more refined samples. You may also have to change your signal processing and learning network. It's important to ensure that a product's model can run in real time on the specified edge device and within its memory constraints. This is certainly important for applications where timely response is critical, like healthcare monitoring. You also have to make sure any end product is designed to handle the wide range of conditions found in real-world scenarios. Our prototype assumes relatively low background noise. However, in real life, you may be using the keyboard in a room with other people talking. You need to think about how best to handle that. Maybe using a DSP filter during feature extraction, or training with a larger data set and one with more types of background noise. You have to consider the physical reliability of your product's hardware as well as the reliability of the learning model and other software. Flaws in both physical and software reliability can not only cause product failure, but injury and liability in critical applications. Maintenance is necessary to ensure that a machine learning model remains accurate and efficient over time. This includes retraining the model, optimizing its parameters, or modifying its architecture. You must establish a maintenance process and allocate the necessary resources to ensure that the model remains up to date and accurate. You must always consider when thinking about bringing a prototype to production whether your application is ethical and whether you are monitoring every step of the way to ensure data, training, and testing are all ethically accomplished. Deploying machine learning on edge devices from prototype to production requires careful optimization, testing, deployment, maintenance, and monitoring. With the increasing demand for edge computing and availability of edge devices, a thoughtful approach to prototyping and producing edge products is more critical than ever. Thank you for spending time with me taking this course. Machine learning is an exciting field, and the explosion of embedded applications on the edge will have tremendous impact that will touch all areas of industry and life. If you'd like to learn more, here are a few resources you might find helpful. Edge Impulse documentation is a good place to look for information about their platform, and they also have an online forum where you can ask questions of the community. TensorFlow is a popular machine learning platform. TensorFlow Lite is designed to help deploy machine learning to embedded or edge devices. In fact, Edge Impulse uses TensorFlow Lite among other technologies on its platform. You can find out more about TensorFlow Lite on their website. Another good source to know about is the TinyML Foundation. It was organized to inform and educate about machine learning on the edge. TinyML hosts events and is a good source of information about the industry.